All right, our next speaker is Richard Smith. Richard Smith is a professor of statistics and biostatistics at the University of North Carolina in Chapel Hill and a former director of SAMC. His main research interests are in extreme value theory and environmental statistics, but with a side interest in statistics of track and road races. For a number of years, he has acted as informal consultant to the Boston Marathon. Today's talk is based on work that grew out of that consultation. So let's thank Richard. Thank you.
Thank you. Okay, good. All right, well, thank you very much. Thanks to Mark and Scott for the invitation to speak. It's a pleasure to be back at NESSIS. For those of you who are regulars here, I did give a talk that was also related to the Boston Marathon a number of years ago at a NESSIS, but this is a different topic. It arose out of the same contacts with the Boston Marathon, but I wanted to talk about a different subject today. It's collaborative in part with two other people who are in the audience, Spencer Siegel, who's an undergrad at North Carolina, and he's developing a senior thesis project based on this, and Dorit Hammerling, a long-time collaborator in both science and running. She's at Colorado School of Mines, and she's also giving a poster later today. Acknowledgements. So this, as Mark just mentioned, it grew out of a long-running collaboration I've had with the Boston Marathon, and we actually spent part of yesterday talking to folks at the Boston Marathon. So I want to acknowledge them, particularly Jack Fleming has been my main contact there since he's the COO of the Boston Marathon, Boston Athletic Association. Tom Grilk is the CEO. And Michael and Chris, Michael was the former data manager and Chris is their current data manager. So the Boston Marathon, like many sports organizations these days, over the years, they've collected masses of data and they're beginning to think about how they can use that data more effectively in managing the race. I also like to mention Scott Powers. At that time at the time we originally did this, he was an undergrad student at UNC, and I think somebody told me he's now working for I think it was the LA Dodgers as a sports analytics person. Jesse Chusisky was also a grad student at UNC. She's now an assistant professor at Yale. And I'm also using some data. There was the talk I gave back in 2013 that was eventually a paper in PLOS One, was a collaboration with Dorit and Jesse and two other people who are both marathon runners and Harvard professors, namely Francesca Dominici and Giovanni Parmigiani. That was a study based on trying to predict Boston Marathon performances in the year of the Boston bombing, when many runners were stranded on the course. And they asked us to come up with an algorithm to predict the finishing times of those runners. So that was what my previous talk was at NESSIS. And I also mentioned that Dorit and two of her current students have a poster on a closely related topic later today. So there were, that was a photograph taken yesterday. So Jack Fleming's the guy in the black shirt, and Tom Grilk's the tall guy. We were there, and we're standing in front of the Boston Marathon trophy. They have an office in Dartmouth Street, and very close to the finish line of the Boston Marathon. So in terms of what we were talking about, well, this is, if anybody here as I know there's at least one person in the audience who has entered and been accepted for the Boston Marathon. If anybody was trying to enter the next spring's Boston Marathon, this was the week when you will have got your notice of either being accepted or rejected. And the way the Boston Marathon works is they have qualifying times, and the qualifying times are down here. They're different for men and women, and they're different depending on different age groups. But the race has been oversubscribed numerous times, and the algorithm they've come up with over the years is that if they're oversubscribed, then essentially they will accept people in the order depending on how many seconds they beat their qualifying time by. So, I mean, this actually shows you what the standard you actually had to achieve to do it. So if you're a man under the age of 34, your qualifying standard was 3 hours, but in practice to get accepted, you had to do 2:58:21. So you had to beat it by at least 1 minute 39 seconds. And if you look at the numbers, you will see that 1:39 actually applies across the board. So in other words, anybody who applied to the Boston Marathon to run it in 2020, who achieved the qualifying standard, you actually had to beat it by at least 1 minute 39 seconds to get accepted. And this is another table that shows how this increment has varied over the years. They first introduced this system in 2012, and that year you had to beat the official time by 1 minute 14 seconds to get accepted. This is the total field size. And over the years, 2013 isn't on here because, in fact, 2013 is the 1 year since they introduced this system that they were able to accept everybody who was qualified. Over the years, it shrunk a bit, and then it grew a bit to last year. The cutoff was 4:52. And at that point, I had a number of phone calls with them over the course of a few days where they said, well, look, we've got to change something. We can't go with this. So we had some consultations about how they should change the standard to try to stop this cutoff phenomenon in the future. And the result of that was that they tightened the standard for 5 minutes, by 5 minutes. So the standards to qualify for 2020 were across the board 5 minutes faster than they were previously, but they were still oversubscribed. They still had this 1:39 cutoff. Now, you might be wondering, well, these are the actual field sizes. You might say, why don't they just accept more runners? And of course, that's what a lot of people think they should do, just accept more runners. But there are physical constraints. They have to negotiate with all the police around Boston. It actually runs through 8 different communities. Boston is merely the last one of the 8. And the roads are, it's not like the New York or Chicago. The New York starts on the Verrazano Bridge, where there's 8 lanes that are normally filled with traffic that they can just use for the runners coming in, whereas the Boston Marathon starts in this small village called Hopkinton, and for about the first 10 miles of the race, you're basically running on country streets where the road is maybe 20 feet wide or something. So there are physical constraints on what they can accept. So most of my consulting with them has been sort of about, well, how would they change the standards to try to manage the size of the field? And when we were there yesterday, we were talking about possible ways of doing this. So here's a bit of the background. Boston Marathon is the only major marathon. The New York Marathon, if anybody's tried to run the New York Marathon, they have completely different systems of qualification and put a lot less emphasis on how fast the runner has run. But the Boston Marathon, which has existed since 1897, they started with qualifying times in the 1970s. And I got involved in 2010. What happened originally was that the entries closed out in one day. And that year, I got accepted myself and was one of those who was scrambling to get onto the website before they closed entries. And after that, I sent them an email saying, well, here are some ideas where these are my ideas how you might solve this problem in the future. And I was genuinely surprised when they actually got back to me, because I was sure there were lots of people making such proposals to them. But Jack Fleming got back to me and said, well, we're interested in your proposal. We'd like to talk about it. So that was how our collaboration got started. Those were the standards as they were back in 2010, basically 10 minutes slower than they are now. At that time, the qualifying time for men 18 to 34 was 3:10. And the standards in 2012 were uniformly tightened by 5 minutes. And then the collaboration we had a year ago resulted in them being tightened by 5 minutes again. But in both cases, those solutions were only reached after considering quite a number of alternatives. So what I want to talk about the rest of the talk is not really about these sort of race management issues, but to think a little bit more abstractly and theoretically about how would we actually try to characterize, if you were starting from scratch, developing a set of standards for runners of different age groups and having both male and female, what would actually be a fair way to develop standards so that at some level they're equitable across all the age and gender categories. And this is not an easy problem, even conceptually, to formulate what you mean by that. There are a number of different ways you could think about the problem that could lead you to different solutions. Now, if you ask most people who run in races and maybe are aware of this problem, but maybe haven't thought in too much detail about how it actually works, the standard answer you get is, well, use age-graded standards. So you see a lot of races these days. People go and they run maybe a 5K race, and you say, well, you did 28 minutes for the 5K race, but your age-graded standard was 75% or something like that. Now, these age-graded standards come from comparing the time that the runner actually ran with either the actual world record for that particular age and gender or some sort of smoothed version of the world records. So, an either actual or nominal world record. But these may not reflect typical runners' performances, and age-graded standards are actually very susceptible to outliers. So, for instance, there was a guy by the name of Ed Whitlock. Now, Ed Whitlock, he died a couple of years ago at the age of 86, but before he died, he's the only runner in history over the age of 70 to run a sub-3-hour marathon. He is also the only runner in history over the age of 80 to run a sub-4-hour marathon. And in both cases, nobody else has ever come close to those standards, at least not yet. And so if you're a man over the age of 70 and you're being compared with Ed Whitlock, that's not really a fair comparison. So what we're trying to do here is to look more. I'm looking more specifically at the age factor than the gender factor. Now, Dorit's poster later today is more specifically focused on the gender factor, but they're obviously closely related things. So let me describe what I'm going to call a longitudinal approach to the performance versus age question. And when I say longitudinal, I mean it in the sense that people use that phrase in medical statistics and epidemiology, where you're trying to follow the performance of individual runners, in this case, not individual patients in a hospital, but individual runners, and trying to see how their performances vary with age. So what I'm going to describe here is a project that originally started several years ago, and at the end of the talk I'll talk about some recent updates. But originally, it's one of the features of the Boston Marathon. They will notice this on their website, that about 500 runners have run the Boston Marathon at least 10 years in succession. Well, at the time we actually started this, they didn't have their data management system quite as streamlined as it is now, so I don't actually have the records of those 500 runners. But what we did, or what I did originally, was I did have some data sets that I had gathered from them over the previous consultations, and particularly had the complete sets of results for the races of 2010, 2011, and 2013, and extended that by using online results to try and extend this to find, and this was my criterion, to find runners who had run at least 6 times if they were men or 5 times if they were women over the time period 2001 to 2013. So this was a manual process. Now, what we're doing now, or what Dorit and her colleagues are doing, is to automate this process using web scraping technology. But that wasn't the original method of doing it. Manually construct this data set, and the runners, since we did have this algorithm we'd used to predict the times of runners who didn't finish the race in 2013. We also used our own predicted times there. And the result of this process was a database of 547 men and 249 women, a total of 806 runners, and 7,219 individual race results. In other words, each of these runners ran a number of times. Some of them had run more than 10 times over that time period, and altogether 7,219 results from 806 individual runners. Now, that's still a relatively small data set. I'm sure there are really many more runners that we didn't detect in our algorithm, and we're hoping the web scraping algorithm will allow us to extend this database. So what's the idea of the approach? Well, for each individual runner, you can think of they've maybe run it 5 times or 10 times over this time, so we have a little bit of a trace from which we can see for each runner a narrow window of how their times have varied with age over that narrow window. And I'm using a color code to distinguish the men from the women, and men are in red and women are in blue. And the question here, the statistical question, is how to combine information across runners. So just to give you an idea how this works. So this is one runner in the database. He's a guy in his 50s and was running a little bit under 4 hours by the look of it. And I know by the time he turned 60, he was getting a bit slower, but maybe not too much. And there are a couple of years he did much better. There's another one, that's a woman in her 30s. There's a second runner, a slightly younger man in his 40s, approaching 50. There's some guy who seemed to have slowed down quite a bit over his late 30s, getting into his 40s. So we can just piece together individual tracks of runners together. And if you put them all in, there we are, sorry, there we are. That's all 806 runners superimposed. Okay. So the idea is, how are we going to take that mass of data and try to get some curves out of it that would actually represent what we might call a quotes-unquote typical runner. But of course, these are all runners who've actually run the Boston Marathon, which means that somewhere they must have qualified for the Boston Marathon. And so it's not really a random sample of all runners. So bear that in mind. It's not easy to define what we actually mean by a random sample in this context. But the idea here is let's build it in what turns out to be a random effects analysis. So let me go to my one slide of equations. So Mark said at the beginning we should all have a slide of equations. So here's a slide of equations, my one slide of this in the whole talk. This is the model. So it turns out if you're looking at running times, it's better to do it on a log scale, and we're representing it as so obviously some runners have better ability than others. Some of those curves were way above others. So we want some effect due to the ability of an individual runner. That's best modeled as a random effect. Now, there's also quite a bit of variation from year to year. And within the time span we were talking about, 2 of the years, 2004 and 2012, were very hot years. Times were much slower. More recently, 2018, this was not within this database, but 2018 was another very slow year, but in that case because of very cold conditions and a strong headwind. So some years are slower than others. So we model that effect with a random year effect, and this is represented as a fixed effect due to age. And the fixed effect is a nonlinear function of age, and in practice we've represented it by splines, though there are other technologies such as kernels and wavelets that you could use if you prefer. And then all of this fits within, it's a random effects modeling, and there's a well-known R package called LME4. And by the way, there's another poster later today, Spencer with 2 of his colleagues who are sitting up in the middle of the audience there, James and Dan. They've applied similar sorts of statistical ideas, but their focus is based on NBA data. So you can look at their slide for some other ideas about how to apply random effects modeling. So the results that come out of this. So the idea is that we take all of this, we take out the random effects due to the individual runners, we take out the random effects due to variation from year to year, and what's left is a smooth function of age. And we're doing it separately for men and women because for obvious reasons, we want to come up with performance curves that are appropriate for both men and women. So this is what comes out of that particular algorithm. And it's a set of curves. So in each case, I'm trying to estimate that age, the time versus age curve. So there are confidence limits, the dashed. So we have separate curves for the men in red and the women in blue. We have point-wise 95% confidence intervals represented by the dashed curves. And they do show some, they follow the overall feature that the obvious conclusion is that as you get older, you get slower, which everybody knows. And also there is, one of the controversies about the Boston Marathon, and Dorrit's poster is more focused on this issue, is that they have a fixed 30-minute gap between women's and men's qualifying time in the same age group. And a lot of people have argued over the years, is that 30 minutes fair? Is it? Some people argue it's favoring the men and others argue it's favoring the women, but it seems nobody actually thinks 30 minutes is actually the right increment, except possibly me. I actually think it's not so bad, but this is a way you could look at it more systematically. So there's, I think on that curve, maybe there's a bit more, there's about a 30-minute difference, at least at that age range between the two bands. This curve has some obvious artifacts. Now, you'll notice, for instance, why do women get faster than men at the age of 75? Well, the obvious answer is they don't. There's very few people of that age range in the Boston Marathon database. So that is almost certainly an artifact. I mean, we're using splines, and most people know splines sometimes do strange things at the end of the range of data, and that's basically what's going on there. It's possible this artifact here is also, something to do with splines behaving strangely at the end of the data. I actually think that's probably more genuine, that runners do tend to improve in their 20s, at least at the marathon level, maybe not at 10Ks, but also I think there might be a sort of a sampling effect there that maybe older runners, or slightly older runners, people who are 30 rather than 20, are more likely to enter the Boston Marathon. I don't know, but that seems to me a plausible theory. There are some other peculiarities, like the somewhat irregular shape of the female curve between ages 30 and 50. But please remember, this is only based on about 250 women and a slightly larger sample of men. So this is still a small sample relative to the whole population of marathon runners. So what are we trying to do to extend all this? Well, what Dorrit and her colleagues have done, they've developed a web scraping algorithm. I'm told it takes quite a bit of work to apply this algorithm, but what they have gradually tried to do is to extend the database, bring in more races, and basically a much larger sample size. So Spencer Siegel has recently started working on analyzing the Chicago Marathon. So this is 8 years of data from the Chicago Marathon. The total size of the data set is about twice what I was analyzing for Boston. So it's not massively bigger, but it certainly is bigger, and you get some smoother curves. And again, there's a bit of a dip in the performances in the 20s, but not nearly as sharply as you saw in Boston. If you look closely at the male versus female distance, it looks as though maybe women are slowing down. Women in their 40s are slowing down a little bit more rapidly than men in their 40s. I don't know whether that's an artifact. We need to look at other races to see if we get the same phenomenon in other races. But you can also see that the direction this is going, that we're coming up with what I think are more realistic curves for these data sets. Now, one criticism of that analysis, I said the Boston Marathon data have this sampling effect. You have to qualify to get into the Boston Marathon. This is sort of suffering from the opposite sampling bias, that A lot of runners in the Chicago Marathon would come nowhere close to qualifying for the Boston Marathon. And so, in some sense, we want to focus this more on runners who have a chance of qualifying for the Boston Marathon. So Spencer's also reran his analysis just on the subset of runners who have qualified at least once for the Boston Marathon. So this perhaps is a bit closer to the kind of the Boston population. Another idea that he's only done this in the last week or so, but another idea we've talked about is to subdivide the group in this particular analysis into quartiles. So you can take those random effects that we were estimating as part of our model, you can order them and break the population into subpopulations according to their random effect. So we get separate curves for different subgroups, and presumably this bottom quartile is the one that's going to be most realistic in terms of Boston Marathon qualifying times. So there's another one. There's the corresponding curve for female runners. Let me skip over this a bit quickly because I'm running out of time here, but we've also done some comparisons where we're saying, well, how would qualifying times derived from this approach compare with either the times that the Boston Marathon are currently using or what they would use if they weren't, some people are still saying, well, Boston should use age-graded performances. And I think particularly on the female curve, the age-graded performances, which is the green curve here, actually leads you to something very different. But that's still a legitimate question for discussion. So let me pass over that rather quickly. Oh, we also looked at the year effect. And as I told you, those 2004, 2012 were much slower years, and that's actually reflected in the random effects we estimated. So let me come to the conclusion. So the problem is difficult. There's not a clear-cut way to do this. The standards have evolved over years, but there's no real science in the sense of anybody trying to do, you might think, well, did they do something vaguely like this back in the 70s when they started doing it? And I don't think they did. And so in that sense, I would say there's no science. No science in terms of systematically trying to compare different age groups or genders. Age-graded standards are popular in the running community, but they have problems. And the longitudinal method here is the only method at the moment we have based on how individual runners' performances change with age. I will just mention that, by the way, there are different ways you could set up the longitudinal analysis, the random effects analysis, and that's something else we're trying to explore. So what we'd like to do, I don't think, I'm not trying to recommend that the Boston Marathon should actually adopt standards come out of this approach, at least not at the moment, but our intention is to keep looking at it, look at other marathons, try to extend the methods, and perhaps come out with something that could be perhaps more broadly acceptable. So that's it, and thank you very much for your attention.
We have time for one or two quick questions. Does anyone have a question? Okay. While you're handing it over, I'll ask a really quick one. So if I understood correctly, you're using in your analysis people who have entered the Boston Marathon across all the years in your study.
Yes.
Okay. Have you considered, just to address some of the selection effects, only using people that have just run in just a handful of studies, and that increases your sample size, but might address some selection issues?
Sorry, say that again. No.
So in other words, if I'm somebody who's only run in years 2012, 2013, 2014,
Yeah.
that's it, enter me into the analysis.
Well, what we started with, this was just the way I was able to construct a database. So the starting point was people who ran in each of those 3 years. But of course, there are many people who've run the Boston Marathon more than 6 times who didn't happen to run in those particular years. So that's why, one of the things that we want to do is to go back and analyze a more complete set of Boston data as well, because the data I was analyzing was just still a limited set of data. Yeah.
Are you concerned at all with survival bias within your sample? If a runner chooses to run an additional year, they're likely to be in the higher subset of individuals at that age group. Are you concerned at all with that?
That's definitely a problem with the Boston, analyzing results from the Boston Marathon itself, because a lot of runners find, this has been my own personal experience, I've got to a certain age, I can no longer achieve the qualifying standards. So my races in recent years have not appeared, I've not been running in the Boston Marathon. But now the idea is looking at races like Chicago, and somewhere along the line we're going to get to New York and a couple of the other larger races, that we would at least reduce that bias. But I don't think there's a way of eliminating it, because at some point people just give up and don't run races at all. And what about the people who actually get injured or sick in some way and they can't run anymore? So you can't eliminate that sort of bias. But I think trying to look at different races and try to combine results as best you can is the best way to go.
Well, let's thank Richard one more time.